July 14th, 2016, Nice, France, 10:33 p.m. A white 19-ton cargo truck is deliberately driven into crowds celebrating Bastille Day, killing 87 and injuring 458 people. This tragic attack is not isolated. It is known as a VAW, or a Vehicle as a Weapon attack, and we can cite many more examples over the past decade, including Berlin in 2016, London and Barcelona in 2017, and an example closer to home, Toronto, specifically on Yonge Street in 2018. One of the simplest ways to mitigate these attacks is by surrounding public spaces with Bollard.
A bollard is a safety device that protects pedestrians from vehicle traffic. Usually it is a pole embedded in the ground between a road or parking lot and a sidewalk or public area with foot traffic.
The idea is that the bollard will absorb the impact of the vehicle's collision and stop the vehicle from damaging buildings or hurting people.
Bollards can be made out of various materials based on various factors such as the number of uses, the impact force to be withstood, the conditions the bollard would be exposed to, etc. Bollards are sometimes made out of concrete, but concrete is highly brittle, has poor energy absorption, and its quality tends to be variable because of mix, curing, cover depth, and rebar placement in the concrete. Polymers, on the other hand, tend to be for low-speed situations. They tend to deform and then get back into place below a certain speed. Therefore, we are conducting our study on metal bollards.
Several standards define vehicle impact performance for bollards, including ASTM F2656, F3016, IWA14, and the legacy U.S. Department of Defense K ratings K4, K8, K12.
The design phase of bollards is pretty typical, starting with rough sketches, moving to 3D models. Then, after the prototype withstands the proper impact resistance and load testing, the bollard is manufactured.
The steel pipe is usually the raw material. The base, cap, and fixture are usually machined and MIG welded to the pipe. The bollard is then inspected for quality. Finally, the bollard is galvanized and given a powder coating for corrosion resistance. Lastly, depending on the application of the bollard, a layer of bright paint is added for visibility.
We will be investigating this bollard from Ontario Bollards, which is made from ASI 304 stainless steel, and analyzing other metals to try and find the ideal one, based on our simplified models and calculations.
Thickness is going to be our free variable, meaning it will vary depending on the material selected. All other dimensions are the same as the ant bollard, so height is 0.9 meters and diameter is 0.275 meters. A typical Mercedes Sprinter, a common truck, has a bumper height around 0.56 meters, so that will be our impact point. We will ignore the material encased in concrete and assume a fixed base.
In terms of functional requirements, a bollard must be able to stop a vehicle from penetrating an area while still allowing pedestrians through. They must be high visibility to minimize unnecessary crashes, and also be able to stay outside exposed to the elements for a significant amount of time without corroding.
For non-functional requirements, the bollard should not take up too much space, be safe, match the environment aesthetically, be as cheap as possible, recyclable, and have as small an impact on the environment as possible.
The cost model of our bollard, we have that cost equals the material constant of cost per meters cubed times the volume. Rearranging the formula for bending moment gives us T, which is our free variable thickness, which we can sub into the volume of the cost equation. Putting out the material constants gives us an MPI of cost per meter cubed over yield strength that we are trying to minimize. If we are trying to maximize, as shown on the Granta plot, we will flip our MPI to yield strength over cost per meter cubed.
We also want to minimize the kilograms of CO2 output and maximize the bending stress by rearranging the formula of bending stress for a free variable thickness and subbing that into the formula for kilograms of CO2 output. We can see that the MPI is the material constant in kilograms per kilogram of CO2, which is divided by the stress. Since density is dependent on the material but not relevant to a bollard application, the critical value cannot be determined, and the MPI line was set where it could eliminate many materials but leave options open for other MPIs to narrow down.
We want to maximize the ratio between stress and strain, or Young's modulus, and also maximize the yield strength of the material. This will limit deflection and increase the amount of force that can be applied before plastic deformation. By rearranging the equations for elastic strain and bending, we get that the MPI equals yield strength squared over Young's modulus.
There are also durability requirements necessary for an outdoor metal object. We applied additional requirements around the material's resistance to freshwater, saltwater, organic solvents, weak acid, and UV radiation. It should also be unflammable and recyclable.
After considering these MPIs, multiple thousands of materials were narrowed down to 300. These 300 materials were ranked by yield strength. Filtering out identical materials with different heat treatments left us with the following list. Nickel cobalt chromium alloy ARX 350, stainless steel martensitic ASI 440C, cobalt based superalloy multiphase MP35N, titanium alpha beta alloy, iron-based chromium-nickel superalloy A286, and finally, the aluminum alloy from Lab 2. The nickel-cobalt-chromium alloy contains 45% nickel, 25% cobalt, 17% chromium, and less than 5% of a number of other metals. According to the yield strength MPI, T needs to be 7.26 mm. According to the bending stress MPI, T needs to be 40.5 mm, or around 4 cm. And according to the stiffness MPI, T needs to be 2.8 mm. Taking the maximum value of 40.5 mm, we calculated the cost to be $17,823.9 and a CO2 output of around 4,926.01 kilograms.
The best heat treatment for this nickel alloy to maximize strength was found to be 53% cold reduction, then aging it at 538 degrees Celsius for 4 hours. After this, the bending stress MPI allows a T of 28.6 mm, which lowers the cost to $12,565.2 and a CO2 output of 3,472.66 kilograms. Martensitic stainless steel 440C is 78% iron, 16% chromium, and 1.2% carbon, and then less than 1% a number of other metals. Solving the yield strength MPI for T gives 7.66 mm, bending stress MPI gives a T value of 33.38 mm, and the stiffness MPI gives a T value of 3.15 mm. Taking the maximum value of T to be 33.38 mm, the cost is equal to $477.93. The CO2 output is equal to 441.5 kilograms. The best heat treatment to maximize strength is tempering at 150 degrees Celsius, then quenching it. After this, the bending stress MPI gives a value of T equal to 28.82 mm. This lowers the cost to $376.40 and the CO2 output to 412.39 kilograms.
The next selected material is cobalt-based superalloy, ME230. This is a multi-phase cobalt-nickel-chromium-molybdenum alloy, often used in aerospace or deep-sea applications. The MPIs give a thickness value of 2.5 mm, which results in a cost of $9,900 and a CO2 output of 3,800 kilograms. To maximize the strength of ME230, the recommended treatment is age hardening after heavy cold work. The alloy is typically cold reduced by about 50%, then aged at around 540 degrees Celsius for 4 hours, followed by air cooling. This ordering and precipitation process increases the strength significantly. After aging, the bending stress MPI gives a required thickness of 1.9 mm, which lowers the cost to approximately $8,000 and CO2 output to around 3,400 kilograms. This alloy is an alpha-beta titanium alloy often used in jet engines. Plugging in the material values into the MPIs gives a thickness value of 5.15 mm. This results in a cost of $3,900 and a CO2 output of 1,900 kilograms. Titanium alloys typically gain strength through solution treating and aging. The alloy is heated to the beta or alpha plus beta region, held to dissolve retained phases, then quenched. A final aging step at moderate temperatures precipitates strengthening phases and recovers hardness. After heat treatment, the bending stress MPI gives a required thickness of 4.3 mm, which reduces the cost to roughly $3,500 and the CO2 output to around 1,200 kilograms.
The next material to be analyzed is an iron-based superalloy composed of 50% iron, 25% nickel, 15% chromium, 2% titanium, and minor amounts of other metals. Plugging in the material constants to our MPI equations gives us a thickness of 3.34 mm, which results in a cost of $2,103.57 and a CO2 output of 1,095.57 kilograms. After this heat treatment, the higher yield strength means bending stress is no longer the limiting case, so the design becomes controlled by the deflection constraint. The required wall thickness drops from 3.34 mm to about 2.5 mm, and because cost and mass both scale with thickness, the estimated cost falls to about $1,600 and the CO2 output drops to roughly 820 kilograms.
Lastly, in Lab 2, we analyzed a 6063 aluminum sample, taking the average yield strength for each aging length, showed that the 18 hours of aging resulted in the highest average yield strength of 258.47 megapascals. Plugging this value into our free variables gives a T value of 228.6 millimeters, which is much bigger than our diameter of 137.5 millimeters. Therefore, aluminum is not a viable option. Based off our material selection and analysis, it can be seen that 440C stainless steel has the lowest cost and CO2 output, while still meeting our strength and bending requirements.
Comparing it to the current steel used by Ant, we have concluded that while they are very similar in cost and CO2 output, Ant's Bollard has a slightly lower thickness and as a result, lower cost and CO2 output, meaning it is the best choice for this application.
This could be due to the fact that Ant buys raw materials in bulk from suppliers that give them a better price on their batches compared to market price.
Thank you for listening to our presentation.